Imagine standing on the platform at Union Station in Washington, D.C. The air is heavy with the humidity of the Potomac, and the hum of electric locomotives fills the cavernous station. You are waiting for the premier experience of American rail travel, the Acela Express. When it arrives, gliding in with its distinctive teal and grey livery, it looks the part of a high-speed machine. Its nose is tapered, its profile is sleek, and it articulates around curves with a mechanical grace that suggests velocity. But looks can be deceiving. Beneath that stainless steel skin lies an engineering contradiction so profound it has baffled international experts for 2 decades. French and Canadian engineers, the very people who helped birth this machine from the lineage of the world-famous TGV, had a different name for it during testing. They didn't call it the Bullet, they didn't call it the Express, they called it the Pig. This wasn't an insult to its aesthetics, it was a statement of physics. A standard French TGV Réseau trainset, the technological cousin from which the Acela was derived, is a marvel of lightweight engineering. It moves with a power-to-weight ratio of approximately 30.8 horsepower per ton. This metric is the lifeblood of high-speed rail. It dictates how fast a train can accelerate out of a curve, how quickly it can stop in an emergency, and how much energy it consumes to push air out of its way at 186 miles per hour. The Acela Express, by contrast, manages a sluggish 22.4 horsepower per ton. This discrepancy is not a rounding error. It is a fundamental alteration of the vehicle's DNA. To achieve the requisite safety standards of the United States, the Acela was forced to gain weight, massive amounts of it. A full Acela trainset tips the scales at approximately 1,246,000 pounds, 565 tons. To put that in perspective, that is roughly equivalent to forcing a marathon runner to compete while wearing a suit of medieval plate armor. The culprit is not incompetence. The engineers at Bombardier and Alstom did not forget how to build light trains. The culprit is a number, buried deep within the Code of Federal Regulations, that has held American passenger rail hostage for nearly a century: 800,000 pounds. This is the required buff strength, the static compressive load that the underframe of a passenger car must withstand without permanent deformation. In simple terms, the United States government legally mandates that its passenger trains be built like tanks. They must be capable of surviving a head-on collision with a freight locomotive while acting as a rigid shield for the souls on board. This requirement, born from the blood and steam of the early 20th century, has rendered the Japanese Shinkansen, the safest, most reliable high-speed train in history, effectively illegal on American rails. If you were to import a brand new N700S Shinkansen trainset from Japan, lower it onto the tracks in New Jersey, and attempt to run it to Philadelphia, you would be breaking the law. It would be deemed a paper train, structurally deficient and unsafe for the American operating environment. This report explores why that is, how a century-old mail delivery rule came to define modern transport, and why the United States is finally, painfully, trying to change its mind. To understand why a modern train needs to withstand nearly £1 million of force, we have to leave the modern corridor and travel back to 1912. The United States was a different world. The interstate highway system was a distant dream, aviation was a novelty, and the railroad was the circulatory system of the entire continent. It was also incredibly dangerous. In the early 1900s, the Railway Mail Service, RMS, was the internet of its day. Information moved by rail, and speed was the currency of the realm. To sort the millions of letters moving across the country daily, the US Post Office didn't just ship mail, they processed it en route. Railway Post Office, RPO cars, were essentially rolling sorting centres, staffed by clerks who spent their shifts standing at tables, slotting letters into pigeonholes while the train thundered down the tracks. Logistically, these cars were often placed at the very front of the consist, directly behind the steam locomotive and its tender. This allowed for rapid loading and unloading at station stops without delaying the passengers further back. But from a safety perspective, this position was the crush zone. Rail traffic in this era was managed by primitive block signals, pocket watches, and human vigilance. Collisions were not just possible, they were a statistical inevitability. When a steam train collided head-on with another or rear-ended a stalled freight train, the kinetic energy had to go somewhere. The rolling stock of the time was primarily constructed of wood. In a high-speed impact, these wooden cars did not crumble gracefully. They splintered. Worse, they exhibited a terrifying behavior known as telescoping. In a collision, the force would cause the underframe of one car to shear off its bogies and ride up over the underframe of the car in front of it. The overriding car would then slice through the superstructure of the victim car like a piston entering a cylinder. For the male clerk standing in that forward RPO car, the result was catastrophic. The wooden walls offered no resistance. They were crushed or sliced apart by the invading train car. The frequency and horror of these accidents forced the hand of the railway mail service. They realized that they could not rely on preventing the crash. The signaling technology and human factors of 1912 simply weren't reliable enough. Instead, they had to ensure the car could survive the crash. They shifted their philosophy to passive safety, survivability through structural rigidity. In 1912, the RMS issued a specification requiring that all new cars used for mail service have a steel underframe capable of resisting a buffer force of at least 400,000 pounds. The logic was brute force physics. If the frame is strong enough to resist buckling, it will stay in line. If it stays in line, it won't override the car in front. If it doesn't override, it won't telescope. The goal was to turn the train car into an unbreakable box. This standard proved effective. Fatalities in RPO cars dropped as steel replaced wood. But as train weights and speeds increased, so did the forces involved. In a 1938 revision, the requirement was doubled to 800,000 pounds. This was formalized in 1945 and eventually adopted by the Interstate Commerce Commission, ICC, for all passenger equipment in 1956. This number, 800,000 pounds, became the holy grail of American rail engineering. It was the barrier to entry. Every passenger car, from the gleaming streamliners of the Santa Fe Super Chief to the commuter cars of the Long Island Railroad, had to be built around a massive steel spine capable of withstanding this load. When the Federal Railroad Administration, FRA, was created and eventually codified modern passenger safety standards in 49 CFR, Part 238 in 1999, they didn't reinvent the wheel, they codified the tank. The regulation stated clearly, all passenger equipment shall resist a minimum static end load of 800,000 pounds applied on the line of draft without permanent deformation of the body structure. This regulation effectively froze American passenger rail design in 1945. While the rest of the world, particularly Europe and Japan, moved toward lighter materials, crash energy management, and active accident avoidance, the United States remained committed to the philosophy of the unbreakable box, and they had a very specific reason for doing so. The persistence of the 800,000 pound rule is not merely a case of bureaucratic inertia. It is a response to the unique and uniquely hostile environment of the American railroad network. In Japan or France, high-speed rail lines are typically dedicated infrastructure. The Shinkansen runs on tracks that are exclusive to the Shinkansen. The TGV runs on lignes à grande vitesse, LGV, that are reserved for high-speed traffic. In the United States, passenger trains are guests on a network built for monsters. The vast majority of rail infrastructure in America is owned by private freight railroads, Union Pacific, BNSF, CSX, Norfolk Southern. These companies make their money by hauling massive quantities of goods. A typical U.S. Class I freight train is a behemoth of industrial capacity. It can stretch for 2 or 3 miles, carrying coal, grain, or double-stacked shipping containers. These trains can weigh anywhere from 10,000 to 20,000 tons. This is the mixed traffic reality. An Amtrak passenger train, weighing perhaps 600 tons, must share the same rails with a freight train weighing 15,000 tons. The laws of physics in this scenario are unforgiving. In a collision between a featherweight passenger train and a heavyweight freight train, the conservation of momentum dictates that the passenger train will be obliterated. The FRA's regulatory philosophy, therefore, has been one of deep pessimism. They assume that active measures will fail. They assume that signals will be missed. They assume that a freight train will be on the same track as a passenger train, and when that inevitable collision happens, the passenger train must be strong enough to survive the impact with a movable mountain of steel. This is passive safety taken to its logical extreme. It is a philosophy that says, we cannot prevent the crash, so we must armor the victim. And this is why the Shinkansen, a train designed with a completely different philosophy, is illegal. While the United States spent the 20th century building better armor, Japan spent the post-war era figuring out how to stop the war. The development of the Shinkansen, the bullet train, was predicated on a philosophy that rejected the inevitability of the crash. This is active safety. When the Tokaido Shinkansen opened in 1964, it wasn't just a faster train, it was a sealed system. Japanese engineers realized that you cannot safely run a train at 200 kilometers per hour, 125 miles per hour, if there is a chance of hitting a dump truck at a grade crossing or a freight train shunting in a yard. The crash avoidance principle relies on two pillars: dedication and automation. Dedication means isolation. The Shinkansen network is fully grade separated. There are zero level crossings on the high-speed lines. Every road goes over or under the tracks. The tracks are fenced off, strictly forbidding public access. Furthermore, Shinkansen tracks are legally barred to freight traffic during operating hours. The heavy, slow, dangerous freight trains run on the separate, narrow-gauge, conventional network. The Shinkansen is a thoroughbred racehorse that never has to share the track with a draft horse. Automation removes the fallible human. In the US, for much of the 20th century, safety relied on an engineer looking out the window for wayside signals, lights on poles that told them to stop or go. If the engineer was distracted, tired, or incapacitated, they could miss a signal, leading to disaster. The Shinkansen eliminated this risk with automatic train control, ATC. On the Shinkansen, there are no wayside signals to miss. The speed limit and movement authority are transmitted directly to the train's computer through the rails. The ATC system displays the permitted speed on the driver's dashboard. If the driver attempts to exceed this speed, or if the train approaches a section occupied by another train, the brakes apply automatically. The train literally cannot violate the safety buffer. The system enforces the physics of separation. The most impressive component of this active safety net is the Urgent Earthquake Detection and Alarm System, UREDAS. Japan sits on the Ring of Fire, one of the most seismically active zones on the planet. A train traveling at 300 kilometers per hour is incredibly vulnerable to ground motion. Even a minor track deviation could cause a catastrophic derailment. How do you protect a train from the ground moving beneath it? You stop the train before the ground moves. UREDAS exploits a quirk of geophysics. When an earthquake rupture occurs, it sends out waves of energy. The first waves to arrive are P waves, primary waves. These are compressional waves that travel very fast, approximately 5 to 8 kilometers per second. However, P waves are relatively weak. They don't cause the destructive shaking. The destructive shaking comes from the S waves, secondary waves, which follow the P waves. S waves are shear waves that move the ground side to side. They travel slower, approximately 3 to 5 kilometers per second. The difference in speed creates a blind interval, a gap of time between the arrival of the harmless P wave and the destructive S wave. UREDAS places seismometers along the rail lines and, crucially, far out on the coast and ocean floor, closer to the likely epicenters. When a sensor detects the P wave signature, it calculates the epicenter and estimated magnitude within 1 to 3 seconds. If the threat exceeds a threshold, it sends a signal to the power substations. The power to the overhead catenary wires is cut immediately. The trains, detecting the power loss or receiving a direct radio signal, apply their emergency brakes automatically. All of this happens before the S wave hits the train. This system was put to the ultimate test on March 11, 2011, during the Great East Japan earthquake, magnitude 9.0. At the moment the quake struck, 27 Shinkansen trains were operating in the affected Tohoku region. UREDAS detected the P waves and triggered the emergency brakes across the network. The result? 0 passenger fatalities, 0 passenger injuries. One train, doing a test run with no passengers, derailed, but the active fleet stopped safely before the violent shaking could throw them off the tracks. In the Japanese philosophy, you don't need an £800,000 steel frame because you have ensured, through billions of dollars of infrastructure and technology, that the train will never hit anything heavy enough to crush it. The safety is in the system, not the shell. When Amtrak sought to introduce high-speed rail to the Northeast Corridor, NEC, in the 1990s, they were caught between these two worlds. They wanted the speed of the French TGV, but they were stuck with the infrastructure of the Pennsylvania Railroad. The Northeast Corridor is the busiest rail line in North America, but it is a mixed traffic environment. It hosts Amtrak intercity trains, commuter agencies like NJ Transit, SEPTA, MARC, and, critically, freight trains. Because the Acela would share tracks with these heavy trains, the FRA refused to waive the 800,000-pound buff strength requirement. Amtrak selected a consortium of Bombardier and Alstom to build the Acela. Their starting point was the TGV technology, specifically the TGV Réseau. But to meet the FRA's tank-like standards, the design had to be fundamentally altered. Engineers added massive stainless steel ribs to the car bodies. They reinforced the collision posts, the vertical beams at the ends of the cars, to withstand 500,000 pounds of shear force. They beefed up the underframe. They added side impact protection. The result was a train set that weighed significantly more than its European parent. TGV Réseau power car weight, approximately 68 tons, approximately 150,000 pounds. Acela Express power car weight, approximately 92.5 tons, 204,000 pounds. This 30% increase in mass had cascading effects on performance. To move this heavier train, the Acela needed more power, but power adds weight, transformers, motors. The power-to-weight ratio plummeted to 22.4 horsepower per ton, compared to the TGV's 30.8 horsepower per ton. This meant the Acela accelerated slower, taking longer to reach its top speed of 150 miles per hour. The most insidious penalty of this weight is not speed, but damage. Trains exert tremendous forces on the track structure. This force is a function of the axle load, the amount of weight resting on each pair of wheels. Shinkansen N700 series. Axle load, approximately 11.2 tons, 25,000 pounds, per axle. Acela Express power car. Axle load, approximately 23 tons, 51,000 pounds, per axle. The Acela puts nearly double the weight on the rail per wheel compared to a Shinkansen. When a wheel rolls over a track, it generates a contact stress. The relationship between axle load and track damage is not linear, it is exponential, often cited as the fourth power rule in pavement engineering, though rail mechanics are complex. A small increase in weight leads to a massive increase in wear. On the Northeast Corridor, this manifested in the destruction of concrete ties. The heavy Acela power cars, combined with the lateral forces generated by high-speed curving, began to grind down the concrete pads that support the rails. This phenomenon, known as rail seat abrasion, caused the rail to widen, gauge widening, creating a derailment risk. Amtrak was forced to replace thousands of ties and impose speed restrictions, slowing down the very service that was designed to be fast. The Acela had another trick up its sleeve that added to the complexity: active tilt. The Northeast Corridor is not a straight line. It is a curvy path laid down in the 19th century following the contours of the coastline. A standard TGV would have to slow down significantly for these curves to prevent passengers from being thrown against the windows by centrifugal force. To maintain speed, the Acela uses a hydraulic tilting system that leans the carriage into the turn, banking like an airplane. This reduces the lateral force felt by passengers, allowing the train to take curves 30% faster than a conventional train. However, this system adds even more weight: pumps, hydraulics, sensors, and complexity. The TGV and the Shinkansen, mostly, do not use active tilt because they don't need to. Their tracks were built straight. The Acela is a technological patch for an infrastructure problem, carrying the heavy baggage of US regulation and the mechanical complexity of tilt to compensate for a track built in the 1800s. For decades, the 800,000-pound rule was the third rail of US transportation policy. Touch it, and you die. But as the 21st century progressed, the isolationist policy became economically unsustainable. The US had virtually no domestic high-speed rail manufacturing base. If it wanted high-speed rail, like the proposed California High-Speed Rail or the privately funded Brightline West, it had to buy from Europe or Asia. Forcing Siemens, Alstom, or Kawasaki to redesign their proven trains into tanks was driving up costs and delaying projects by years. In November 2018, the FRA finally blinked. They issued a landmark rule change. Passenger Equipment Safety Standards, standards for alternative compliance and high-speed train sets. This created a new category of passenger equipment, Tier 3. Tier 3 was a surrender to physics. It admitted that crash energy management, CEM, the European/Asian standard, was a valid alternative to the unbreakable box. CEM works on the same principle as a modern car. Instead of a rigid frame that transfers the entire shock of impact to the occupants, like shaking an egg in a steel box, CEM designs the vehicle to die so the passengers can live. Specific zones of the train, the nose, the vestibules, the ends of the cars, are designed to crumple. This controlled deformation absorbs the kinetic energy of the crash, slowing the deceleration and cushioning the occupied areas. Under Tier 3, a train set can be certified if it demonstrates equivalent safety to a Tier 1 train through CEM, even if it doesn't meet the static 800,000-pound buff strength. This allows for lighter, aluminum-bodied trains that are aerodynamic and energy efficient. But there was a catch. The US rail network is still a mixed traffic monster. The FRA wasn't willing to let a lightweight plastic and aluminum train go head-to-head with a freight train at 220 miles per hour. The regulation stipulates a critical operational limit: speeds greater than 125 miles per hour. Tier 3 trains must operate on exclusive, grade-separated right-of-way. No freight trains, no level crossings. This is the Shinkansen environment. Speeds less than or equal to 125 miles per hour. Tier 3 trains can share tracks with freight and conventional trains, Tier 1. This shared use provision is the key. It allows a high-speed train to run fast on new dedicated tracks in the countryside, and then slow down to 125 miles per hour to enter the city on existing legacy tracks shared with freight. This is a compromise that attempts to bridge the gap between the European ideal and the American reality.